Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are currently looking at Chapter 5, Thermodynamic Processes and Cycles, and specifically we are looking at vapor compression refrigeration. In our last lesson, we went through the steps of how you would do vapor compression refrigeration calculations. In this lesson, we'll be looking at actually doing an example problem. First of all, need to show you kind of what the data is presented as. In our textbook, it's presented graphically, not as a data table. So it's going to mean that our answers are not always going to exactly agree. Some examples. So this is identified in your book as R134A, but this is actually DuPont refrigerant 422A. This is R134A from another source. This is Freon 22 or R22. And this is R12. Now these are not the only refrigerants that you might run into, but these are four of the traditionally more common refrigerants that you might bump into. They all sort of have a similar shape to the graphs, and we will be using one of these in this next example. Here we have a vapor compression refrigerator that uses R12 as the working fluid. So I have found a graph for that. The pressures in the evaporator and condenser are 400 kilopascals and 1400 kilopascals respectively. The refrigerant exits the evaporator with 3 degrees C of superheat and exits the condenser after being cooled to saturated liquid. The compressor is 85% efficient. Determine the coefficient of performance. I want to go over first a reminder of where the equipment is and our basic assumptions that we need to make. So step 1 to 2 will be our evaporator. And in the evaporator, we will assume that delta P is equal to 0. Next is going to be our compressor. For the compressor, we will assume that ideally delta S equals 0, and we'll do that for our first steps. We'll come back and use the the compressor efficiency next. After the compressor is our condenser. For the condenser, we are assuming again that delta P is equal to 0. And finally, we're going to go back to our original state with a Joule-Thomson valve or a throttling valve, many names that you might call this one. For this valve, delta H is going to equal 0, all right? So these are our basic facts that we're going to be working with. I've taken now, we know that we're operating between 400 kilopascals and 1400 kilopascals. So I have added red lines here to indicate those two pressures. And we're going to use this so that we can find all of the necessary data. If you have a data table for this, or you might find a version online where you can put in the temperature and pressure, for instance, and have data provided to you, you might explore those options also. But if we are doing this from the graph, our values are going to be a little rougher. The low pressure is going to be states 1 and 2, so 400 kilopascals, and 1400 for states 3 and 4 are higher pressure points. Okay. Now, where can we begin? Well, one I know is that state 4 is going to be the high pressure saturated liquid. And so this is going to be state 4, and that value looks like it is about 58 degrees C. And the enthalpy is about 258. Now I am not going to read the entropy, but you could also try and read the entropy off from, these lines that are going up this direction. I'm not doing that, okay, not with this graph. It's not really very good for that calculation. I know that to go from state 4 to state 1 is constant enthalpy. So state 1, therefore, is also going to be 258. This will be therefore state 1. Okay. The temperature there is 10 degrees C. It's probably a little under 10, but 10-ish degrees C. We are then going to, it says it's going to exit the evaporator, so state 2, with 3 degrees C of superheat. Okay, I chose this example simply because this is something that we haven't really run across yet. So this would be saturated. 3 degrees of superheat means I'm going to go 3 additional degrees. And if you look at those, it means I am just right about there. So I've moved over 3 degrees, and the temperatures are marked down here on this scale. Okay, and these curves going up. So it's not very far over. So this is going to be, state 2 is 13 degrees C. And that looks like about 345 for the enthalpy. And then my ideal is constant entropy. And that line takes me to approximately there. Okay, very close to there. And so it's about 380. Okay, now this is using the graph. I also do have, however, tables available to me. And like I say, there are places like the NIST, the National Bureau of Standards, it's NIST. They have data tables that you can look things up electronically. When I did that, I have a more complete set of data that I'm going to fill in here. So if I went through and did those same steps using data tables instead of the graph, these are the values that I obtained. But you can use either one. You'll get very roughly the same answers either way. But we start our calculations typically with the ideal compressor and then use the compressor efficiency to turn that over into an actual work for our compressor. The ideal work is going to be the delta H across the compressor, so therefore it's 432.8 minus 406.5, or 26.3 kilojoules per kilogram. Okay. The actual work of the compressor is going to be using the efficiency, so 26.3 divided by the efficiency of 0.85 tells me that the actual power for the compressor is 30.9 kilojoules per kilogram. This I use to find H3 actual. So 406.5 plus 30.9 gives me 437.4 kilojoules per kilogram is the actual exit to the compressor. Now I do want to take a moment here and point out that if you'll recall when we were doing our pumps, the pump was like 1/10 of this much work required. It is always easier to pump a liquid to a given pressure than it would be to take the same amount of vapor and compress it to that pressure. So for a given delta P, you're better off doing a pump with a liquid rather than a compressor. So, okay, little side note there. Let's next look at our the cold temperature, so the evaporator. The evaporator is QC, which is H2 minus H1, and in this case it is 131.1 kilojoules per kilogram. Okay, this is the amount of cooling achieved. Okay, if we look at our condenser is H4 minus H3 actual, which is going to be negative 162 kilojoules per kilogram of heat lost by the cycle. Our coefficient of performance, or omega in this case, is going to be 131.1 divided by 30.9. We want the actual. And so we end up with a coefficient of performance of 4.24. As I noted before, we want to make sure that this is a value not limited by being between 0 and 1. In fact, it probably will be greater than 1. So this concludes this example. In our next video lesson, we're going to look at some other variations on refrigeration example where we choose different refrigerants and see how those choices might affect things so that we will be prepared to make decisions in the future. Thank you very much for your time.